heartland of America, the gateway to the West. This is Engineering Tomorrow, the podcast, keeping you entertained and in the know on the latest commercial and industrial heating, cooling, and water treatment technologies.
Welcome to Engineering Tomorrow. I am your host, Brian Gomsky, again for our 5th episode. And we have a very special guest today, Jeff Henderson with Midwest Machinery St. Louis, the sales manager, is here. Someone I've been trying to get on the show for several months now. The schedules haven't worked out, but he's carved out a few minutes today to grace us with his presence. Jeff, you're kind of a big deal in the industry. Tell us a little bit about yourself.
Thanks, Brian. I'm glad we're able to get together. Thanks for having me on. Like you said, I'm sales manager here for the St. Louis office, sales manager / sales engineer. I've been working for Midwest for 11 years now, been in the industry for, going on 14. So it's flown by, but been here for a while.
That's great, Jeff. Today we are going to be talking about heat pumps. And I'm going to be honest, I do not have any questions prepared.
Okay.
So we're going to be kind of flying off the cuff here. I'm going to be asking you some very tough and difficult questions, and I'm going to test your knowledge on the subject.
Good, let's do it. I'm excited for the challenge.
So in every episode, I start out with the most basic of basics. What is a heat pump?
Well, it's a good question. First, what we're, I think, going to primarily talk about today is the water source heat pump, where you're using water to cool the condenser instead of air, which is what you would typically see at your house. You have a condensing unit outside with a fan and a coil that uses air to cool that condenser. What we're going to be talking about is water source heat pumps, where you have a cooling tower or a geothermal well, and you're pumping water through the water source heat pump unit to cool the condenser. So now getting that out of the way, let's talk about what a water source heat pump is. Primarily used in hotels, apartments, condos, dormitories, things like that, where you have several individual cooling zones. For instance, a condo, you might have 200 or 300 units, and instead of putting in a chiller in the basement and pumping water out to individual fan coil units, you use water source heat pumps, and there's several advantages to that. Number one is energy, because you can move heat around your building, because you might have some of the outside zones that need cooling and some of the inside zones that need heating, and you can take that heat from those outside zones and move it to the inside zone. So there is some big energy savings with water source heat pumps. Alternatively, redundancy. If you have a chiller in the basement and that chiller goes down, every single one of your condos is now without air conditioning. Whereas with the water source heat pump, the compressor is in the unit itself. So you have, in essence, 200 or 300 compressors on the job. So if one compressor goes down, just that zone does, and it does not affect the other zones in the building. So there's redundancy, there's energy, there's ease of installation. Those three things are really what's great about water source heat pumps in general.
All right, so we've got individual heat pumps per room, I guess you could say, right?
Well, per room or per zone. If you think about it like a small apartment or a condominium, you're not going to have a heat pump in every room. You'll have one per apartment. So you might have it in a closet out in the corner of your living room, and then it's ducted up to serve the bedroom, the bathrooms, the kitchen, and the living room.
So we got water moving, in and out of the building. Is there refrigeration? I mean, is there actual refrigerant within each one of these units, or?
Yeah, so the refrigerant, the evaporator and the condenser in a water source heat pump is all combined into the one packaged unit. You don't have, like VRF, you do have the condenser outside, and that is usually has refrigerant lines pumped into the building. This is all contained inside the box. You're moving water around the building, not refrigerant. So the evaporator, the condenser, the compressor are all contained within the unit itself.
So you've got a compressor essentially very almost in the room, maybe behind some drywall or something. What do they do to curb the noise? 'Cause you think in your house, you go outside by your air conditioner, you got that loud compressor. What are some of the things they do to make sure they keep that as quiet as possible?
Yeah, that's a good question. At your house, you do have the compressor noise, so you can hear it. But you also have that condenser fan outside that you're hearing. So that's a motor that's very loud. But that being said, the compressor does make noise. So I think most manufacturers, water source heat pumps, do some things with the compressor. They put some isolation underneath the supports of the compressor to keep the vibrations down. Most manufacturers also offer an ultra quiet option, and that consists of double-walled insulation around the compressor compartment, and also putting some sort of sound blanket over the compressor itself. So most manufacturers nowadays have gotten pretty good at isolating that sound, so you don't even notice it.
Okay. What are some things as an occupant that on maintenance side, is that something, I mean, how much maintenance do these require from an end user versus how much maintenance is required having your service group yearly on these types of units?
So these types of units, like any piece of air conditioning equipment, it's going to require service at some point in time. For instance, we here in St. Louis, we have a local hotel who's got, I think, close to 300 of these units installed. And what they typically do is, of every size, they'll keep one spare. So if something goes wrong, a compressor goes out, or a fan motor goes out, or a control board goes out, they simply take their spare, install it, take the broken one down, and take it down to their shop and work on it down there. And that allows them to keep the room open to be rented to customers. So they're not losing any money, while they wait for that repair. They also keep, spare parts, compressors of every size, maybe a fan motor of every size, maybe a coil of every size in case one springs a leak. But like any other piece of equipment, you're going to have, over the years, you're going to have some kind of replacement or parts or something's going to need to be replaced. But not any worse than any other type of equipment. The difference between a water source heat pump and a large chiller, though, is significant. Most building operators don't know how to repair a chiller compressor, which could be 500-600 tons. That's a very large and complex piece of machinery. Whereas it's pretty easy to swap out a compressor or a fan motor, relatively speaking.
What's the yearly maintenance? Is it just replacing the filters and then letting it run, basically? Yeah,
I mean, routine maintenance, you're probably doing a couple things. You're changing out the filters just like you would at your house. But you're probably also doing some kind of system checks as far as refrigerant pressures, making sure that you're not low in refrigerant, you don't have a leak somewhere. You can also, a lot of the hose kits for the water that's coming in and out of the units, they put Y strainers on them, and that keeps dirt out of the unit itself. So those periodically need to be changed or emptied out and checked. Other than that, just checking refrigerant pressures, and most units now have a diagnostic tool that you can just hook right up to the unit, and it'll tell you what those pressures are.
What do you tend to typically see in grade schools and high schools? Is that water source heat pump? Is that what they normally use, or?
Yes. So specifically, elementary and middle schools in the suburbs where there's more land, a lot of them will use the excess land they have, whether it's a football field or a parking lot. And while they're building the school, they'll actually drill geothermal wells. So instead of using a cooling tower to cool down the water that's going to the water source heat pumps, they'll use the energy of the earth, which is consistently right around 60 degrees, to cool the water down in the winter. In the summer, and warm it back up in the wintertime. So that offers really, really high efficiency. So paybacks on that is somewhere in the neighborhood of 10 to 15 years when you're doing a water source geothermal system.
What do you call you call the end unit like the terminal unit, or you call it the heat pump?
Typically, they just call it a heat pump. You can call it a terminal unit. That's usually kind of reserved for, I think, VAV boxes. So I call it water source heat pump.
What do you tend to see lifespan of a individual heat pump? When do you need to start considering replacement?
Usually we see about 15 years is the life expectancy of a water source heat pump. They're pretty good about the big parts of a heat pump, or the compressor, the fan motor, and then the brains, the controls, and the refrigeration pieces. Usually if a compressor goes, you just switch out a compressor and go on your way. But when you start losing compressors and you start losing your refrigerant piping, starts kind of corroding away and getting leaks all the time, then it becomes more cost effective to just replace the whole unit.
Mm-hmm. I'm going to go into a little bit of a controversial topic here. Okay. So, heat pumps versus VRF. Tell me, that seems to be, you ask 100 people, you're going to get 100 different opinions. Tell me the difference between the two and the benefits.
It's a good question. I think they both have their advantages and disadvantages. Specifically, water source heat pumps, the advantages that you have there is you're pumping water around your building and not refrigerant. So what the water source heat pump manufacturers will tell you is water source heat pumps are better because you're not having a safety issue with refrigerant lines in your walls, that if someone drills a hole in the wall, punctures a refrigerant line, springs a leak, that could be potentially dangerous. Not to mention you would have a very hard time of finding that leak to where you could repair your system. VRF, though, also, it offers close to the same efficiencies as water source heat pumps without the need for cooling tower and water and pumps, because they're air cooled. So they have, just like your house, they have condensers outside. They're very high powered condensers. And then they run the refrigerant lines like they do in your house throughout the building to the various fan coils that are in each zone. So that's what the VRF manufacturers will say is, hey, you don't need a cooling tower, you don't need pumps, you don't need all these water lines. Will you just run some condenser lines back and forth from our unit? We'll give you pretty good efficiencies.
Okay. In general, I mean, efficiency-wise, are they going to be about the same? Is heat pumps better?
That's an ongoing question. Since it's difficult to rate a VRF unit because of the variance in refrigerant lines and how far it's going away and back, it's kind of hard to compare. But ASHRAE at their headquarters building, I don't know, about 7 or 8 years ago, when they were building their new building, installed VRF on one floor, and on an identical floor installed water source heat pumps with a geothermal well. And comparing geothermal to VRF, geothermal blew it out of the water in energy savings.
I would imagine.
Yeah, so geothermal compared to VRF, it's not even close. They also did an energy model of that same building if they had used a cooling tower instead of the geothermal well. And in the article, it said that they still would beat VRF, but by not as much. So, okay. So you got to weigh the options and what's best for your building. If you are doing a renovation and you don't already have pipes and the building layout doesn't allow for a central pumping plant. Water source heat pumps might not work, and VRF might be great. Vice versa, it might also be a building where VRF doesn't work, but water source heat pumps would go great.
Going back to heat pumps, tell me about the different piping configurations and options we can go with.
So, when you have water source heat pumps, the typical way that it's installed is two pipes, a supply and return going through your whole building. So you've got two pipes, and actually three if you have a condensate drain that needs to go. Many times that's just taken care of right at the unit, but you run two pipes throughout your whole building. So a supply line going out to the heat pumps, usually around 87, 88 degree water going to the heat pumps, and then the return line coming back to the mechanical room, usually around 97, 98 degrees. So that's the typical layout. You'll have a heat exchanger usually, or a fluid cooler. So normally on larger buildings, it makes more sense to go with a heat exchanger and open cooling tower. So that heat exchanger on what we call the loop side, which is serving the heat pumps, will see that 87, 97 degree water. And then on your cooling tower side, you'll have 95, 85 that's actually cooling the water. And you have that heat exchanger because you want to keep your water source heat pumps from seeing the debris that tends to collect in condenser water from a cooling tower. So you isolate that using the heat exchanger. Now, that's system A. In the last 10 years or so, a new type of configuration has come out called single pipe. So instead of bringing 87 degree water to every single heat pump and then putting it back into the return line, you run just one pipe. So the first heat pump on the loop sees 87 degree water. The last heat pump on the loop might see 94 degree water. And that's perfectly okay. That last heat pump on the loop is obviously not going to be as efficient as the first one on the loop, but many times if it's a hotel or something like that, you don't really care if it's not as efficient. If it can't make the duty, you just bump it up one size. The savings comes from the materials and labor of running that second pipe. So by eliminating that, you're cutting back on a lot of upfront cost. Your main loop pumps are also getting smaller because you don't have to overcome the head pressure of all the heat pumps. Every heat pump will now have its own little itty-bitty circulator that will pump the water through the heat pump and back to the loop. So we've seen a lot of contractors use VE to win projects doing that method. An engineer, CM Engineering, I believe, out of Columbia, Missouri, has also done many projects using that method.
Now, with single pipe, can you only have heating or cooling, or is it you can have both?
You can have both.
Okay.
I guess you're saying, can one unit have heating and one unit have cooling? Yes, absolutely. So okay. In fact, you get all the same benefits of that you had before with moving heat around the building. In fact, it might be even easier to do it with single pipe. So absolutely, one unit can be in cooling, one can be in heating. It's not like a two-pipe fan coil job.
You see a lot of PEX pipe in residential. Has that made its way over to commercial? Is that acceptable to run, or are they still running copper?
Most of them are still running, from what I've seen, copper.
Okay.
PEX is starting to make its way, but from what I'm seeing, it's been mostly copper or steel.
Oh, okay. Tell me about do you ever have to drain the water in the loop, or how long does the water last within the system, or is it constantly draining, replacing?
On the cooling tower side, it's constantly being evaporated. So you need to treat that just like you would any cooling tower project. So you're going to have to blow down just because you're going to have a buildup of deposits and minerals in the water. On the loop side, it's a closed loop. So unless you have a leak, you shouldn't have to make up that water very often. So typically when they first start the job, they fill and flush and maybe do that 2 times just to get all the pipe debris and whatever from installation out of the water. After that, it should remain relatively full and not need to be flushed again for quite some time.
Okay. Okay, Jeff, how do you, let's say we decide we want to go with a heat pump or we're in the preliminary stages, how are you going to size your job and your equipment?
So it's different. Everybody kind of has their own different way of doing it. When I'm working on a project, I think what we tend to suggest is you first, obviously, you do your zone checksums for each individual zone to figure out what size heat pump you need. You might find out one room needs a 1-ton unit, another room needs a 1.5-ton unit, and so on. So if you have 300 units on a project, you go in and you add up the heat of rejection on all those units for the cooling side. So not just the load in the room, but you got to take the heat of compression into account too. So you look at the heat of rejection of all those units, add them all up, and let's just say it gives you 300 tons of cooling necessary for those units. You can do, once you have that number, you can do a couple things. You could say, okay, I'm going to size my plant to handle all 300 tons. I'm going to size my cooling tower for 300 tons. And that's safe. That gets you what you need to handle all those units. But what you're saying when you do that is, I think every single one of my heat pumps is going to be on in cooling mode at the exact same time. And that just never happens. So typically what we suggest is you add in some multiplier for diversity. Typically what we see is a 0.8 or a 0.85. And by doing that, you're saying, okay, at worst case scenario, I'll have 85% of my units on in cooling at the same time on a design day. And if you do that, you're not going to have any problems. You're going to be able to support all your heat pumps, and you're probably going to put a little bit of redundancy in anyways once you get to your plant. So if we've got 100 tons of cooling, we're going to size our plant for about 85, just to be safe. So once you get there, now you're going to go look at your plant. Okay, so I have 100 tons of cooling. I have to size my cooling towers for 85 tons. So most places put some sort of redundancy in. So I'm not going to do 100% redundancy. I mean, you certainly can if it's an important, maybe it's a luxury condo, and if one cooling tower goes down, you want to be absolutely certain that on a design day it can handle the whole load. So if that's the case, then you would size probably 2 cells of cooling tower, each size for 85 tons. That way, if one goes down, one can handle the whole load on design day. Typically, from there, what we see is you take that 85 tons, which is already 85%, and you multiply that by 0.75. So what you're saying there is my cooling towers, each cell will be sized for 75% of my worst-case scenario. So it gives you a good amount of redundancy, almost 100%, but maybe call it 97% redundancy, and saves you a lot of money up front. So you're not oversizing your equipment. And then you do the same thing on your boilers. You look at your the heat you needed for those heat pumps and add them all up, times it by 0.85, and boilers going up one size usually doesn't cost you that much. So you just size each boiler for 100% of the load, and then run them in parallel, and you'll be fine. Same thing with pumps. Typically, we see duty standby. Constant speed on the cooling tower side. If we always suggest you put drives on to balance because you're going to save money there, but you're typically going to run your cooling tower pumps constant speed, and then your loop pumps are going to be variable speed based off differential pressure.
All right, Jeff. I heard you mention a couple different pieces of equipment here. Again, we've laid out the job. Tell me about every part and piece we're going to need to install this equipment, because I know it's not just the heat pumps. You know, give me the whole kit and caboodle that we need to see here.
The whole kit and caboodle. So, you got a heat pump job. You're going to need water source heat pumps, obviously. Then you have to look at your plant. You're going to need loop pumps. So these are the pumps that are going to pump the water around to each individual heat pump. We typically do those duty standby, so if one goes down, the other can pick up the whole load. You're going to need cooling tower pumps for the other side of the heat exchanger to pump the water through the heat exchanger and up to your cooling tower. You're going to need that plate and frame heat exchanger. Instead of doing a heat exchanger open tower, you can also do a fluid cooler. We typically see above about 100 tons. It makes more sense to do open tower with a heat exchanger, and it's easier maintenance. And then you're going to need, obviously, the cooling towers if you don't have a geothermal well. And you're going to need some boilers. Typically, since your temperatures are so low, we're using condensing boilers on water source heat pump jobs. So do 2, maybe 3 boilers that can handle the load. Other than that, you're looking at hose kits for your water source heat pumps. Those are flexible stainless steel hoses that connect the heat pump to the actual piping in your loop. They allow for easy install and removal of the heat pump if you need to service it. And they also have isolation valves, usually a PT port so you can test pressure and temperatures if you need to. They have some sort of auto flow or circuit balancing valve so you get the right amount of flow through each heat pump. And sometimes they will have a two-way motorized control valve so that if the heat pump's not on, you don't have water going through it, and that'll help you save money on pumping costs. Other than that, that's pretty much the whole kit and caboodle there.
Okay, great. And then on every job, you personally go out and start up every heat pump? Is that
I
accurate?
personally, yes. Every heat pump job, whether it's 10 of them or 300 of them, I personally spend over 2 hours on each heat pump starting them up.
And you also, Jeff will also sign each heat pump too. So
I will.
That's a benefit.
Well, I'll personalize it too if you want.
Jeff, it has been fantastic that you came here. I'm glad we could finally both find the time to sit down and talk about heat pumps. And moving forward for our listeners, we are going to definitely be more regular with the podcast. We got a lot of stuff going on in the background, some new content on our website we're working on. But tune in next time for another exciting episode of Engineering Tomorrow.
You've been listening to Engineering Tomorrow, the podcast. For more insights and downloadable content, please visit our website at www.engineeringtomorrow.blog. Until next time, engineer for tomorrow, today.